So first of all, thank you, Britpay, for the opportunity to present the wonderful project which we are doing at University of Nottingham. It's about predicting concrete payment performance. I'm Sampath Kumar, a PhD student working with Dr. Nick Tom. So in this presentation, I'm going to give you a quick background about the project, and I walk you through the objectives and the methodology of the project. Then I'll present some results and finally with the conclusions. So to give you a quick background, I believe all of you already know about the Concrete Legacy program launched by National Highways, and you know the vision of the project, the 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 intent the project has been launched. So National Highways has asked University of Nottingham, and it funded University of Nottingham to work in the similar lines to achieve the vision. So this project mainly intended to give some trustworthy scientific solutions for managing the roads. Obviously, to manage the roads, we need to have a good scientific prediction models for the concrete payments. So this project has started with the major objective, with the broad objective to develop a trustworthy method of predicting the future performance for the concrete payments. And when I say predicting the future, we will have some models where the inputs will be obviously from the site, maybe traffic, maybe from the climatic parameters, and also the existing slab characteristics of physical characteristics of the payment. And the output will be in a form which will help which should help the national highways for its decision making process for the maintenance of the concrete roads. So, though we have a major big broad objective, we have sub objectives to achieve this objective. First one is to review what are the existing payment iteration models for the concrete payment around the world. And secondly, to collect the required data, we have different set of sources, and to collect and compile the data from those sources. And the third objective is to identify which modeling approach has to be adopted for this project. And the next one is to develop the prediction model. After you identify the approach, we develop the model by using that approach. And finally, we validate the model, and if it requires any calibration, we calibrate the model. So in a nutshell, it is like review, collect, identify, develop, and validate the model. So we have devised a very very detailed methodology, but I'm here just present you the methodology related to the modeling of the concrete payments. We have three parts here. First one is we are going to follow the empirical methods. Second one is the analytical equations, which is mostly dealing with the theoretical equations, and the numerical solutions. We are using the finite element modeling for getting the numerical solutions. So once we validate and calibrate, as I said, and we develop the model. So I have divided this into the three parts, as I said. First, I will be talking about the empirical modeling. So when I say empirical modeling, we have basically used the machine learning approach, machine learning methods to develop some models. But of course, the most important thing is we need to have the data. So we have used the long-term payment performance from the US to develop some equations, and we also observe which parameters are mostly affected for which kind of different types of distresses. And the beauty of this data set is that they have a time series data they have collected from the long time, maybe 2 to 3 decades. And we have a good set of data which will help us to know the pattern of the deterioration for the different distresses. So, of course, when I say distresses, there are many types of distresses in the concrete payment, but basically we are focusing, in this project, we are focusing on 5 major distresses, which is spalling, longitudinal cracking, transverse cracking, stepping and faulting, and IRI. You can see the stepping and faulting is still in progress, so I've just downlighted it or instead of highlighting it. So, but I'm going to present you the results for the 4 other distresses like spalling, longitudinal cracking, transverse cracking, and IRI. So, and the machine learning methods which we have used for this is we have used 3 methods, which is decision trees, random forest, and deep neural network. And I'm just showing you for longitudinal cracking what are the different variables we have used. So when I say model, we have some independent variables and some dependent variables. Independent variables for the longitudinal cracking which we have used. For the material properties, we have used the compressive strength, elastic modulus, tensile strength, and density of the concrete. And for the physical characteristics, we have used what is the thickness of the concrete surface, thickness of the base layer, what is the age of the pavement, and what is this joint spacing, and different climatic factors like temperature, precipitation, and freezing index, and also the traffic. So when we have these parameters, we could able to predict what will be the length of longitudinal cracking in the future. So similarly, these are the different feature variables for the other types of distresses as well, which we have followed. So for spalling, you can see these are the different independent variables or the feature variables. Similarly for transverse cracking and IRI. So basically, we get how many number of slabs that are spalled, or what will be the length of longitudinal cracking or length of transverse cracking, or what will be the current IRI, or at least in the future IRI. So these are my dependent variables, or these are my predictors. So what we do is we take a data set and we divide it into a training data set and testing data set, where we take 80% of data to just train the model, and we take 20% of data to test the model, how well the model is performing. So for random forest, these are the results for transverse cracking, which I'm showing. R square is the coefficient of determination to just give you an idea how accurate our model is. For the training data set, we got around 0.97 R square score, whereas for testing data set, we have got around 0.85. Similarly, for decision tree, of course, we have some issue of overfitting for whenever we use the decision tree for the training data set, but for testing data set, we got around R square of 0.76. Similarly, 0.99 for training data set when we use the artificial neural networks, and 0.87 when we use it for testing data set. So this is for transverse cracking. Similarly, we have some results for longitudinal cracking, which is almost around 0.89 for the testing data set. So testing data set is more important rather than training, because this is what we are validating our model. Similarly, we have it for spalling and IRI. I'm just showing the testing data set. Of course, the results are not so good, but still I'm showing which we are trying to improve these models by adding more feature variables. So finally, the reason why I'm showing these curves is by using this data set, we could able to predict in the future what will be spalling, or what will be the similarly what will be the cracking when we give set of independent variables. So I'm coming to the second part now, which is numerical modeling. And here we have used the finite element modeling to supposedly simulate the joint, because joint we consider as one of the weakest portions of the concrete pavement. So we have tried to simulate the joint of a concrete pavement and see how the pavement behaves when there is a repeated application of load. So this is our model, what we have taken. So we have subgrade base layers, and there are two slabs, slab 1 and slab 2. Here you can, as you see, these are two half slabs which we have tried to simulate. The dimensions you can see, and we have also provided the double bars along this joint. And the second step in this modeling is to mesh the model. When I say mesh, in the finite element modeling, we divide the entire model into n number of finite elements. So that's why we call it as finite element modeling. So, but the question is how many number of elements we should divide. So that is called model meshing. So for this, we have conducted some mesh convergence study, and we have arrived the optimum mesh size and optimum number of elements that has to be conducted. And we have also conducted a parametric study for the model by changing the different parameters. For example, we have seen how the pavement behaves with and without dowel, and we have also seen when there is different types of joint openings, when it is a very hairline opening or a very wide opening. Similarly, what happens when there is a bound base and unbound base? What happens when there is change in the slab thickness, change in the load case 1, 2, 3, 4, load case 1, 2, 3, 4. I'll just going to explain in the next slide. Results of first study, like what happens when there is a double and when with double and without double, we try to do it in the finite element analysis with the different joint spacing or joint openings, in fact. So when there is a very wide opening, you can see very less load transfer, which is around 6.5%. And you can see when there is a slab, when there is load on one slab, there is very less load transfer in the other slab. So similarly, when the joint opening decreases, you can see there is decrease in this increase in the load transfer efficiency. And when we have introduced a dowel, so here is when we have introduced dowel, so you can see there is a big increase in the load transfer efficiency up to 85%, even if there is a wide opening. So this is the impact of how dowel creates in the concrete pavement. Similarly, we have also studied what happens when there is different load at different locations of the slab. So if the load is close to the joint, we have a kind of deflection, or we can say displacements. And when it is moved away from the joint, you can see the deflections also moving. And when there is exactly on the like a symmetric case of a joint, you can see there is a perfect bowl shape like you see in asphalt pavements. So this is for the concrete pavement with the load and different locations of the load. And we have also studied what happens when the concrete pavement with bound base and without bound base for different load cases. So you can see clearly this is, I'm going to go it fast, this is a linear relationship where you have more stresses if there is an unbound case, or you have less stresses if there is bound base. And one interesting study I would like to highlight here is the damage analysis. We have conducted this damage analysis just around the doubles. If you see, just around the doubles, we have tried to decrease the material property. We have tried to decrease the stiffness of this material just around the doubles, and to see how the pavement behaves when there is a loading. So here, similarly, we have observed the results on both the slabs, slab 1 and slab 2, and interestingly, we have decreased the E value or the stiffness value from 28,000 to 2,000 in various steps, and we could clearly see that there is increase in the strains, which obviously means there is increase in the stresses, and the pavement is more likely to deteriorate when there is traffic loading. And this is at the same study and the same observation at the interface of the slab and dowel. So these are the compressive strains. With the decrease in the modulus value, you can see increase in the compressive strains as well. So this is part 2, and the part 3 is about the analytical modeling, which we have conducting, which is purely on the theoretical base, and we are intending to develop a tool or maybe in a form of a spreadsheet for the industrial use. And these, of course, these theoretical calculations which we have made will be validated or calibrated by the finite element modeling as well. So here, it's still in the development stage, but we intend to develop, or we intend to calculate the aggregate interlock, double embedment, double bending, bound base effect, slab bending under load. And of course, we also want to calculate the incremental damage to the deterioration of the aggregate interlock. What happens when there is deterioration of the aggregate interlocks over the period of time? And at the same time, what is a concrete happens, and what are the stresses around the dowels? What happens if there is a base deterioration, and how it happens? And what is how the crack propagates in the concrete slabs? So these are also intended to develop, but as I said, it's still in the developing stage. So to give you a small glimpse of it, this is the parameters which we are going to input, and we can calculate the deflection. For example, if we are just taking off the dowel from this, so I'm just making it 0, so you can see there are more, the deflections have increased. So these are purely, as I said, on the theoretical calculations, and which we will calibrate it with the finite element analysis. So this is a full length of analytical tool, and you can see we have calculated the crack growths at different levels, and we have also tried to see what are the stresses around the dowels for the various cases. So this is about the analytical tool. So I think I've pretty much covered everything, and these are the conclusions. As I said, we have done the empirical modeling, and we tried to developed some machine learning algorithms for 4 distresses: paralleling, longitudinal cracking, transverse cracking, and IRI. The next big step is that we are trying to validate this with the UK data, if possible, so that we can use it for UK as well. And also, we have conducted the finite element analysis numerical study, and as I said, the findings were found to be satisfactory. Yet we are trying to validate this with the experimental studies. And also, we are currently working on the simplified analytical tool, which I've shown you earlier. So, yeah, this is all from my side. Thank you.